So, in the last module we discussed sequential consistency model, and in this module we are going to discuss the total store order and relaxed consistency models. So, we know that from the sequential consistency model that we need to consider the program order, we need to consider the write completion and write atomicity. And once we put these conditions, then the overall performance will be degraded in the system, and also we may not utilize the hardware performance optimization techniques efficiently. So, for example, consider a scenario where we have the write buffers in our processors from the hardware point of view, and these write buffers are mainly helpful for performance improvement. The reason is whenever there is a store instruction, then processor can write this store value onto a write buffer, and from the processor point of view this store operation is said to be completed once we write that to the write buffer. And so after that we can take the instructions from this store buffer or write buffer and we can send it to the caches and so on. So, but if we consider sequential consistency model in our system, then we cannot use this write buffers. So, this write buffer concept is going to create a problem with respect to the sequential consistency model. So, we will see an example here. So, consider a 2-core system where in core 1 we are going to execute a store instruction followed by a load instruction, and similarly in core 2 also we are going to execute a store instruction followed by a load instruction. So, now for example, if we have write buffers in our multi-core system, what is going to happen is when core 1 is executing this store instruction x equal to new, then it will store this instruction in our store buffer, and so whatever the value written onto the store buffer may not be immediately reflected or communicated to the other cores. So, as a result, when core 2 is executing its load instruction R2 equal to x, it will read the old value. Here the assumption is both the caches associated with this core 1 and core 2 have initial values of this x and y as 0. So, now because the store operation from core 1 is not communicated to core 2, so as a result core 2 is going to read value 0. Similarly, store operation of core 2 is not communicated to core 1, so as a result load operation in core 1 is going to read the old value. So, when we have write buffers in our multi-core system, and if we assume that we have an invalidation based cache coherency protocol, so let us say if core 1 is performing a write operation, so according to cache coherency protocol, so it cannot immediately write to a particular block, it has to send an invalidation signal to all the cores in the multi-core system, and once it gets the acknowledgement from all the other cores stating that they have invalidated their copies, then this core 1 is going to perform the actual write operation. But waiting for this acknowledgement to receive will take longer time. So, and it will waste the processor cycles for core 1. So, as a result one of the optimizations what we can do here is we can consider write buffer, so that this core 1 is going to write this value to the store buffer and it proceeds with the subsequent instructions, and as soon as it gets the acknowledgement for the invalidation signals from all the other cores in the multi-core system, then we take this store instruction from this write buffer and we write it to the actual cache. So, this is the whole the operations we are going to perform when we are dealing with the store instructions. But now if we consider sequential consistency model in our system, sequential consistency says that we have to strictly follow the program order between all the memory operations. So, store to load, load to load, load to store, and store to store. We have to consider strictly this program order. As a result, when core 1 is performing a store operation, it cannot proceed with any other subsequent instructions until the store is said to be completed, and that is going to degrade the overall performance. And so, as a result, in order to utilize these write buffers for performance optimizations, then we have to relax our sequential consistency model. So, in this particular example we actually consider 2 cores and each core is performing a store operation followed by a load operation, and assume that the hardware is supporting the write buffers. And now when each of these cores having the write buffers and whenever they perform a store operation, and so the store operation will be written to the write buffer, and it is not actually communicated to the other cores. So as a result, when core 1 is performing a store operation, this x equal to new is not communicated to core 2, and when core 2 is performing a load operation, it can load the old value. Similarly, when core 2 is performing a store operation, so core 1 can read the old value for that corresponding variable, and that is going to violate our sequential consistency expectations. According to sequential consistency, in this particular case, we are supposed to get R1 and R2 as new and new, but here because of this write buffers, we may get values of 0 and 0, where 0 and 0 are the initial values for x and y. So that is mainly because, so this store is performed or written to a store buffer, and this store buffer cannot be read from the other core. Similarly, this store is going to perform to its corresponding write buffer, and the contents of this write buffer cannot be read from this core. So because of this, so our the expected outcome will be different with respect to the sequential consistency model. But now the question is whether we want to go for sequential consistency or whether we want to utilize the hardware performance optimization techniques or not. Generally, the processor vendors will go for this hardware based performance optimization techniques, and they want to consider relaxed consistency models so that programmer can expect more than whatever the possible outcomes that will be available with respect to the sequential consistency model, so that the programmer will expect extra outcomes in addition to our sequential consistency model behavior. So now in order to utilize write buffers in our processor, now we have to see what is that we have to relax in our sequential consistency model requirements, so that we can come up with a new memory consistency model. So here actually once we have write buffers, our whole idea is each of these processors can proceed with the subsequent load operations which are following the previous store operations, because these store operations are written to store buffer, and it is not actually communicated to or written to the actual cache, and before communicating to the actual cache or before communicating to the other cores, we want to proceed with the load instructions. So that means here we want to go ahead with subsequent load instructions after any store instruction. In other words, we want to relax one particular order among the sequential consistency, that is store followed by a load. If we relax that, then we can expect this 0 0 as one of the valid outcomes for this piece of code. So that is what the total store order memory consistency model says. So here the TSO requires that each core preserves the program order of its loads and stores for these 3 conditions, but not for this. If you have all these 4, then this is exactly same as sequential consistency model, but in total store order, because we are going to exploit write buffer concept for performance improvement, so we relax this particular condition. In place of this, we actually consider write buffers, and we also consider these write buffers are performing in FIFO order, first in first out order when we are writing to the write buffer. And so we still enforce load to load order, load to store order, store to store order. But whenever there is a store followed by a load, then we can perform the subsequent load operation before actually completing the previous store operation. So that is the relaxation we consider, and that is the reason why this is also called as one of the relaxed consistency model compared to the sequential consistency. And sequential consistency is a rigid consistency model, and that is going to degrade the overall performance. So that is the reason why we are considering this total store order, and most of these x86 based processors are actually using this total store order memory consistency model in their systems. So, consider an example. So, here core 1 is performing a store operation, storing a value new into memory location x, and after that it is performing two load operations, loading the value stored in memory location x to R1 register, and similarly loading value stored in memory address y into register R2. Similarly, core 2 is going to execute this piece of code where it is writing a value new to a memory location y, and after that it is going to read a value stored in memory location y to register R3, and after that it is going to read a value which is loaded in memory address x to register R4. And we also assume that initially x and y are 0 and also R2, R4 are 0. So, now if we expect let us say R2 and R4 as 0 and 0, then our expectation for R1 and R3 also 0 and 0, but that may not be the case because we have our cores equipped with the write buffers, and because of this write buffer, so our outcomes will be slightly different. So, here because when we are performing this store operation, the store is written to the write buffer, and after that there is a load instruction from core 1, and this load is to the same location where the previous store is performed. And so, when we are executing this load instruction, what we do is we actually go to the write buffer and see if there is any matching request or not. If there is a matching request, then we can supply that value to the corresponding register, and then that register will be now loaded with the latest return value from that particular core. But this value is there in the write buffer, and this write buffer cannot be read from the other core. So, as a result, when this core is actually trying to read the value from the memory location x, it is going to read the old value only. And the same logic, so here when it is performing a store operation, this store will be written to a store buffer and a store or a write buffer, both are used interchangeably, and when it is performing a load operation to load the value from the same memory address location, then it is going to get the value of new from the write buffer associated with this core, and this write buffer contents cannot be read from this core. So, as a result, when the core 1 is going to perform the second load operation, it is going to read a value 0, that is old value. So, as a result, with this a piece of code executed on a multi-core system where each core is having a write buffer, then our outcomes will be R2 and R4 are 0 and 0, but R1 and R3 are new and new. Again, so here we assume that each of the cores has a write buffer, and also we are considering a total store order mechanism. So, when we consider a total store order memory consistency model, so before this store is said to be completed, we can proceed with the subsequent instructions, and when we perform the first load instruction, it can get the value from the write buffer, that is also called as a bypassing logic. So, it is effectively this load is going to get the value from the write buffer, and this is a load bypassing. So, we just get the value, and the subsequent load, which is L2, which is going to read the value from its cache. So, that has the stale value. So, as a result, we are getting this. So, note that this write buffer is not going to create any problem when we consider a single core system, because in a single core system, whenever we have a load operation, this load is going to get the latest return value to that particular location. The reason is, whenever we have previously a store instruction, the store can be written to the write buffer or a store buffer, and after that if there is a load instruction, this load will first consult the write buffer. If there is a match, then the value will be supplied. If not, then it will go to the next level cache and so on. So, as a result, in a single core system, write buffer is not going to create any problem, even when you have a sequential consistency model. But whereas in the case of multi-core system, when we have write buffers, write buffer contents can be available only to the associated core, but not to the other cores. That means we cannot access the write buffer of core 1 from core 2. because these write buffers are not visible to the other cores. If you want to make these write buffers of each core to be visible to the other cores, then the design will be very complex, and so we cannot go ahead with that particular type of design. So in summary, so we can use the hardware optimization technique for performance improvement in terms of write buffers, so that processor will not be stalled for completing the store operation before proceeding with the subsequent operations, and also we can relax our store to load ordering, so that we can come up with a new memory consistency model, and that is called as a total store order memory consistency model. And once we have total store order memory consistency model, as a programmer we can expect the other outcomes also, and here any subsequent load to a store operation, if both are to the same location, then we can get the value from our write buffers. So as a result, the programmer will add the corresponding outcomes also as part of his expected list of outcomes for the piece of code he is dealing with. So now we will formally define the TSO, total store order memory consistency model. So here the TSO says all the cores insert their loads and stores into the global order respecting their program order. So each of the cores will insert their load and store instructions in the program order, especially when we are dealing with the load to load, load to store, store to store. So that is what is given. For example, if you have a load operation followed by another load operation, but these two load operations are to different locations in the program order, then in the global order also it will be coming in the same order. So if load from a location A is coming before load from location B in the program order, then in the global order also load from A will come before load from B. Similarly, if load from A is coming before a store from B in the program order, then in the global order also a load from A will come before a store from store to a location B. Similarly, if there is a store operation to a memory location A comes before a store to memory location B in the program order, then in the global order also store to a location A comes before store to a location B. And because in the TSO we are actually considering the write buffers, so we consider FIFO, first in first out based write buffers here, so that any subsequent load wants to read, then it is going to read the latest return value, and every load gets its value from the last store before it to the same address. So that is nothing but the value of a load from a memory location A will be the latest store to that particular location in the global memory order, or previous store to the same location in the program order. So actually this second component is talking about bypassing, whereas this talks about the global order. So this store can be from any other core. So this part is same as the sequential consistency model, but because in our TSO we are using a write buffer, so as a result we are actually adding this component also. That means our load can get the latest return value either from the other cores or from the same core. So that is what is the overall meaning of this particular sentence. And if we want to enforce strict order between a store and then a load, then we have to use a fence instruction, and this fence instruction will be an addressless instruction. And so once we have this fence, all the instructions before this fence from that particular core needs to be completed in the program order, and it cannot proceed with any other instructions subsequent to this fence until all the instructions before this fence are completed in the program order. So that is what the meaning of this. For example, if there is a store instruction to a memory location A which is coming before this fence instruction in the program order, in the global order also the store instruction will come before the fence. So, that is effectively we are following the store to fence order, and similarly if there is a fence instruction coming before a load instruction from a memory location A in the program order, then the same thing will be reflected in the global order also. So, fence will come before the load instruction in the global order. So, that is going to say fence to the load ordering. So, whenever we want to strictly enforce that the previous store needs to be visible to every other core, then we have to consider a fence instruction immediately after that store. So, that when we are going to execute a subsequent load, this store is already available to everyone, and then as a result so we can strictly enforce our load to store order. In other words, if you want to come up with the sequential consistency model on top of TSO, all we have to do is we can insert a fence instruction between store and load, if store and load are coming one after another in the program. And note that when we issue a fence instruction, it is going to affect only within that particular core where we are actually executing this fence instruction. For example, if fence is issued in core 1, this fence instruction is not going to affect the ordering of the instructions in core 2, core 3, core 4 or whatever the other cores, but whereas it is going to affect the ordering of instructions in core 1 only. So, now when we want to implement the TSOs, then what we can do is we actually add extra buffer, that is called as a write buffer or a store buffer, so that all stores will come to the store buffer, and processor need not wait for this store instruction to be completed, and it can proceed with subsequent load instructions. And if any subsequent load is actually matching with the previous stores, and if the previous store is there in the store buffer, then we can bypass the value and the load can be getting the value from the store buffer, so that the processor can proceed with subsequent instructions. And whenever the cache coherency system is taking care of the invalidation signals and so on, and then we can start writing these values from the store buffer to the actual cache. And if we want to strictly enforce this store to load ordering, then we have to insert a fence, so that when we insert a fence, for example here in the code that is executed on processor P1, then immediately all the instructions that are there in the store buffer needs to be written to the cache. Then only we can proceed further with the remaining instructions following the fence instruction. In other words, whenever we insert a fence, we have to drain our store buffer. When I say draining the store buffer, we have to take each instruction in the FIFO order, and then we have to write it to our the subsequent caches in our cache coherent memory system. So, that is the reason why. So, when we are using fences, we have to be selectively use these fence instructions, otherwise like it is going to degrade the overall performance. Whenever there is a necessity, then only we can go for fence instruction, otherwise we can just not insert any of these fence instructions in our program. When we have the store buffers, and if there is a context switch happen, and at the time of context switch we have to write the values of the store buffer to the caches. So, we cannot use these contents for a subsequent thread which is executed on any of these cores and so on. So, effectively, so whenever we issue a fence instruction or whenever there is a context switch, thread context switch, then we have to ensure that we drain the store buffer. So, this statement clearly says that during the thread context we have to drain, otherwise like the subsequent thread may read the values from the store buffer and that may be wrong. So, in other words, one thread context should never bypass from the write buffer of the other thread context. So, now we will see the other relaxed consistency model, and before that we are going to give an example why we want further relaxation in our memory consistency model. So, consider two core system where core 1 is executing 3 store instructions. One is writing value new to memory location data 1, another one is writing new value to another memory location data 2, and third one is writing set value to a flag memory location or variable, does not matter. And similarly, core 2 is executing 3 load instructions, but it also executes a condition instruction or a branch instruction, where this branch instruction checks whether R1 is equal to set or not. If it is not equal to set, then it will again go back to this load first load instruction, and it will be in the infinite loop. And when R1 is equal to set, then it is going to execute L2 and L3. So, here both the data 1, data 2 are initially 0 and flag is not equal to set, and now we will see in what way we can execute these instructions in our program. If you see core 1 code, especially these two instructions are independent, S1 and S2, we can execute this S1, S2 in any order. Of course, we cannot execute this S3 before this S1 and S2, though these three store operations are independent, but if we execute S3 before S1 and S2, then what is going to happen is our R2 or R3 may get the old value, that is 0, but according to the programmer's intuition. So, the idea is, so when we execute this instruction, the last store instruction, his idea is these two instructions are already executed, so that when we come to this L2 and L3, then these are going to get the new value. So, this is what his intention when he writes this piece of code. So, as a result, we have to execute S3 after this S1 and S2, but there is no need of executing S1 first and then only S2. We can execute S2 first and after that S1, and finally we can execute S3 and so on. Similarly, in this core 2, so here it does not matter whether we execute L3 first or L2 first among these two instructions. Of course, when we come here already the condition is false, so as a result we come here, but when we come here we can execute this L2 and L3 in any order, it does not matter. So, programmer's expectation is either S1 executed first followed by S3 followed by L1 followed by L2, or he expects S2 should be executed first followed by S3 followed by L1 followed by L3. So, as long as the program is executed like this, he is going to get the expected outcome, so everything is fine. But if you are considering a sequential consistency model or total store order model, then it clearly says that if there is a pair of store instructions, then we have to strictly follow the store to store ordering. So, that means if you consider TSO or SC, then we have to execute S1 first, then only we can go for S2, then we can go for S3. And also sequential consistency on TSO requires that load to load order also should be maintained. So, it means L2 should be executed first, then only L3 can be executed, but this is actually not necessary according to this piece of code. As long as if S1 is executed before S3 or S2 is executed before S3, so he will get the expected outcome, and so everything will be correct. So, there is no need of strictly enforcing order between S1 and S2, similarly L2 and L3. So, this is what is expected, but when we have SC or TSO implemented in our systems, then automatically we require or we force the instruction to be executed in this order, and that is actually not necessary, and that is going to degrade, that may degrade the overall performance. For example, if this store is, let us say, incurred a miss, then subsequent store cannot be executed until the previous store is completed and so on. So, that is actually degrading the performance. So, as a result, when we want to go for performance improvement mechanisms, then we need to further relax some of these conditions. So, when we relax these conditions, then we can come up with a new memory consistency model, so that programmer will reason his program according to this relaxed consistency, and accordingly he will expect a set of outcomes. And then also at the hardware side, we can use optimization mechanisms to exploit out of order execution or independent instruction executions, and so that the overall performance can be improved. So, we can come up with an exampled relaxed consistency model, we can name it as XC, and here we assume there is a global order exists among all the memory instructions and so on, and we also use a fence instruction similar to the TSO, and so this fence will not specify any address, and also it will not affect the order of memory instructions or memory operations in any other core other than the core where we are actually applying this fence instruction. And so whenever we want to enforce the ordering among the instructions, we can separate this pair of instructions with a fence instruction. So effectively, if you have a load and a store, and if you want to execute this load first and after that store, then we will insert a fence instruction between this load and store. So effectively, once we have a fence instruction between any pair of memory instructions, all the instructions before the fence should be completed before we executing any instruction following this fence instruction. And this relaxed consistency model maintains total store order rules for ordering two accesses to the same address only. This is actually says that if you have a load instruction to a same location where there is a store operation performed previously, then this load has to get the value from the previous store. But if the load is to a different location as compared to the previous store, there is no need of enforcing store to load order in that. So that is what we are actually mentioning here. So only when there is a necessity, then we will order the instructions, otherwise we are not going to enforce any ordering between any of the memory instructions. So in other words, XC maintains the TSO rules only for the accesses where these accesses are to the same memory location. So because of that, loads can immediately see updates due to their own stores in the corresponding store buffer, so that loads can get the value from store buffers, and if the loads are to a different memory location as compared to the previous store operations, we do not have to keep our load operation to be waiting until the store operation is executed or whatever. So now consider this example again. So according to the programmer's idea, so he wants either S1 to be executed before S3 or S2 to be executed before S3, but he does not care about the ordering among S1 and S2. Similarly, he wants L1 to be executed before L2 and L1 to be executed before L3, but he does not want the ordering between L2 and L3. So there is a typo here, it should be L3, load 3. So now, because he does not want ordering among this store 1 and store 2, similarly load 2 and load 3, what we can do is we can put a fence instruction here and here. Once we put a fence instruction here, that indicates that, so we do not care about how the ordering of these operations in execution, but when we want to execute this instruction, these two should be completed. In other words, any instruction which is coming after fence can be started executing only when all the instructions which are before this fence instruction said to be completed. Similarly, here whenever we want to execute either L2 or L3, so it is compulsorily required that L1 should be completed, but after that it does not matter whether we execute L3 first or L2 first. So that is what the meaning of this. And now once we put these fence instructions, then it is according to the programmer's expectations, and we will get the expected outcomes. So once fences are there, it ensures that S1, S2 will be executed before this fence, and after this fence only S3 will be executed. And also after that we are executing this L1, which is loading the new set value, and after loading the new set value automatically this condition is false, then we will execute the fence instruction, and after that we can execute L2 and L3 in any order. Because here S1 and S2 are separated by comma, this indicates that it does not matter how S1 and S2 are executed, whether S1 is executed first or S2 is executed first. But whereas if we have this S2 arrow F1, that indicates that S2 should be completed before the fence instruction, and similarly F1 and S3, that means this fence instruction should be executed before executing this S3 instruction. So this is the overall idea of the fences in XC. So, once we have this XC, then we can define this relaxed consistency model formally. So, here this says all the cores insert their loads and stores and fences into the global order respecting these conditions. If there is a load or a store from to a location A which is coming before a fence instruction in the program order, then the same load and store will come before this fence instruction in the global memory order. Similarly, if fence is coming before a load or a store from or to a memory location in the program order, then this fence should be coming before the corresponding load and store instructions in the global order also. And also, if there is a fence instruction which is coming before another fence instruction in the program order, then this fence instruction should be coming first as compared to the other fence instruction in the global memory order also. And also, all the cores insert their loads and stores to the same address into the global memory order respecting their program order. For example, if there is a load instruction coming before a store instruction to the same memory location, then this should be followed in the same global order also. And similarly, if there is a store instruction to the same memory location and which is coming before a load instruction or a store instruction to the same memory location in the program order, that also again we have to respect in the global memory order. Here X and Y are representing load or store instructions. So, here every load gets its value from the last store before it to the same memory address. This is again same as our TSO requirement. So, here we can get the latest store from any of the other cores, or if the same core is actually written a value to the same memory location, then it can, the subsequent load can get the value from the write buffer associated with that particular core. So, that is what is mentioned here. So, this rule is same as the TSO. Effectively, this relaxed consistency model is same as TSO as long as our memory operations are to the same memory location. If these operations are to a different memory location, then we do not have to enforce strict memory ordering between this load and store operations. So, we can reorder the instructions, and whenever there is a necessity to enforce an order, then we will use a fence instruction for that particular thing. So, in order to implement this XC, we actually consider reorder buffer associated with each of the cores, and actually this reorder buffer concept we have already discussed as part of our superscalar processors. And according to superscalar processor design, so we can execute instructions in out of order fashion by exploiting the instruction independence, instruction level parallelism, and also we can exploit the functional unit availability, so that independent instruction can be executed in an out of order fashion. But finally, when we are committing the instructions, we have to commit the instructions in the program order. So, that is where we actually make use of this reorder buffer. Whenever we are issuing an instruction to a functional unit, so we are actually making an entry in the reorder buffer, and the instruction can execute in any order with respect to the other instructions in the program. But when we are committing the instructions, we will commit the instructions from the head of this ROB, so that all the instructions will be committed in the program order. So, that is the overall idea of this reorder buffer, and once we have this reorder buffer mechanism in our hardware, so in order to use this, then we have to consider a relaxed consistency model. But whereas if we consider sequential consistency or TSO type of thing, then we may not exploit this reorder buffers, and so as a result the performance may not be improved significantly. So, in summary, we started with the sequential consistency model where we cannot use our write buffers or reorder buffer mechanisms, and we have to strictly enforce ordering between load stores, stores load, and stores and load. So, that will degrade the overall performance. So, as a result we will relax some of the constraints, that is ordering between store and load, so that we can come up with the TSO, total store order, where we can use the write buffers available with our processors, so that we can improve the performance slightly. And again, in order to further improve the overall performance by exploiting our out of order execution using the reorder buffers, then we have to relax all these memory orderings wherever there is a possibility. So that is where we come up with the relaxed consistency model. And here in the relaxed consistency model, if there is a requirement to be following the order, then we can insert a fence instruction, and otherwise we can execute instructions in out of order fashion by using this reorder buffer. So with that, I am concluding this module, and also this concludes the entire course. And in this multi-core architecture module, so we have discussed several things, and so I will just summarize here. So in order to improve the performance, so we can go for multi-core systems rather than considering single core systems, so that we can exploit thread level parallelism in our programs. And once we have multi-core systems, then all these multi-core applications will go to the main memory to get the data and so on, but because we already discussed a memory wall problem where the performance of processor is significantly increasing compared to the performance of memory. So in order to bridge this memory wall problem, we need to consider multi-level cache hierarchy system. And again, when we are dealing with the shared memory systems in multi-core systems, then what is going to happen is there may be an issue with the cache coherency, there may be an issue with the synchronization, there may be an issue with the memory consistency. So when we have a shared memory multi-core systems, we have to deal with the cache coherency, we have to deal with the synchronization, we have to deal with the memory consistency. And in the last module and this module, the last week and this week, we have considered several techniques associated with the cache coherency maintenance, so synchronization, and the memory consistency models. And as part of the cache coherency, so we discussed three-state cache coherency protocol to maintain the coherency among multiple private caches where they are having the replicated data in their private caches and so on. And we discussed that for bus based systems as well as for the directory based cache coherency protocols. And in order to support the synchronization, so our ISA's instruction set architecture needs to support various hardware primitives, so that when we write software algorithms to deal with the synchronization, then they can make use of these hardware primitives. And similarly, when we deal with the memory consistency, so we know that the memory consistency is different from cache coherency. Even the systems may not have cache coherency, but the systems need to have memory consistency. And as part of the memory consistency, we discussed sequential consistency, we discussed total store order consistency, and relaxed memory consistency models. And among all these three consistency models, so relaxed consistency model will make use of the hardware components available in the process to improve the overall performance. And so that is the summary of this multi-core architecture, the modules. For this, the cache coherency, synchronization, and memory consistency, so we covered the material from these two books. Thank you.